With what I believe are most of the shortcomings identified in my first power supply, it's time to make power supply number 2. Two big differences. The first is the power for the fans is now isolated from the other supplies, and not isolated from the DC power coming in. If I do end up implementing fan control, I'll put a couple of optocouplers on the fan interface board. The second, I'm planning on putting linear regulators on each of the 4 voltage rails. That should really reduce the switching ripple on the supply rails, especially the 12-volt line. That will hurt the efficiency a bit, but the entire isolated supply output should end up being under 2 watts, so other than add a bit more heat to the power supply board, really shouldn't matter much. Now, part selection for a project can be quite fun, can waste a lot of time, but I've always kind of enjoyed that part of a project. The lack of parts being in stock has added a bit of frustration to it, but that does seem to be getting a little better. I started with the fan power section, so first thing I need is a buck regulator. I looked at a few different parts, but I end up picking something I'm familiar with. This chip meets the requirements I want, 30 volt plus input voltage, an enable function, and can easily supply the 200 milliamps I need. While I haven't used this part before, I've used the 16 volt version of this regulator quite a few times, and by increasing the value of the output inductor, they work quite well at much lower output currents. Since this will either be off or supplying about 200 milliamps, I will probably use the AP63201. I ordered both the AP63200 and the 63201, so I'm covered either way I decide to go. One other main part for this section is going to be the inductor. Here their parts tables show a 10 microhenry for the 12 volt output, though I found this statement down here to be quite important. The largest value I have of these is the 47 microhenry. I'll probably start with that and see how it does. I'm thinking I may need a bit more inductance than that, but I'll try with what I have and go from there. So the fan power section should be something like this. The input and output capacitors are the other very important parts, but ripple is not really much of an issue for the fan supply. I just want it to be stable and not feed much noise back into the DC input section. I'll try a small ceramic and a polymer on the output. I was a bit surprised at how uneven the current draw is on the fans, so I'm going to add a bit more capacitance than what the ripple would require. I'll probably make a little adjustment to these parts. I'll probably go for a 12.5 volt output, bump it up just a bit. That way, even with very thin wires, I'll still be at over 12 volts at the fans. For the isolated voltages, I was going back and forth between a TI chip and this one. The main reasons I ended up going with this chip are 1, the pinout is the same as the larger version of this chip I used in the first power supply, so I can put this in the same PC board and do some transformer test. That's a big plus. We'll save a few weeks of time and a test PC board at a minimum. 2, I already have a few of these on hand, ordered them when I ordered the Mac 17691, the 7 watt version of this chip. 3, I'm already familiar with how to do the design with this type of controller, at least enough to get it working. So it won out over me wanting to try the TI chip. I'll try the TI chip next time. By far the most important part of this section is the transformer itself. After I had ordered the pot cores for the first power supply, I found out about RM cores. They still have a circular winding area, easier to get multiple windings out of the core compared to the pot cores, and come in some pretty small sizes. So I ordered a couple of sets of each of the 3 smallest core sizes, and some of the coil formers that were in stock, and this time I did get the core material right. While I knew the transformer core I would need for this transformer would be smaller than the last, it's pretty easy to put in the values and get a better idea of what I need. So I'm wanting 2 watts of output. I'll go with 4.5 watts of apparent power for the transformer. For the flux density, I'll use the maximum listed on the core loss versus frequency chart from the N87 material datasheet. Now for the window utilization factor, I'll go with 0.3. If it's a very small core, I won't be able to get quite that much copper in the core, but it seems to be a good starting point. Frequency, I'll set at 100 kHz. That is the minimum frequency the flyback controller will run at, so it's a worst case value here. So about the smallest core I could use has an AP value of 0.00469 centimeters to the fourth, and I have these 3 cores to choose from. Even the RM4 low profile core is plenty big, AP value-wise, but I've got 5 windings to put in this transformer. And the different voltages I want out of it will put a limit on how few of turns I can use. That, and I only have 30 and 34 gauge magnet wire at the moment. Means it's going to be a tight fit, if it will fit. Now the RM5 seems to be just a tad bit smaller than the pot core I used in the last power supply, so I'm positive there will be plenty of room in it. The RM4L is only about 1.5 times the size I figured. If I can get the windings to fit, it will be the best choice, especially since the core former I have for it has 10 pins. Really, it's just what I was looking for. But I have my doubts about being able to get all the windings in it. The RM5 is for sure overkill. If I had a 10-pin core former for it, I would just go with the RM5. Space difference is not really a factor here, but I only have 8-pin core formers for the RM5. Still enough if I used a common winding terminal? Decisions. I decided to give the RM4 core a try. One of the main reasons for sticking with the Max 17692 was so I could test the transformer. After doing some figuring, looks like I'm going to need 19 turns for the primary. Could get away with 18, I'm sure, but if I can't fit 19, probably won't be able to fit 18. The secondaries look like this. For the 14-volt line, I'll need 13 turns. The 5-volt line will need 5 turns. The positive and negative 7 volts will need 7 turns each. The object here was not to get as many windings as possible to be prime numbers, but for sure none of that is getting divided down. I'm going to use 3 strands of 34 gauge wire for the 5-volt rail. I figured each strand of number 34 wires should be good for 80 milliamps. Going to use 2 strands for the 19 primary turns, and 1 strand for all the rest. I'm using Kapton tape again to gap the transformer core. I put tape on both pieces to start with, and with tape on both it added 0.1 millimeters of gap to the cores. The thing is, I wanted a 0.1 millimeter gap for total gap length, and this turns out to give me 0.2 millimeters total gap, so I removed the tape from one of the core pieces. Of course, it's nice not having to make up a holder for the transformer. Being able to get the core former and clips speeds up the process a bit. It's so small it is hard to get the little clips in place, but makes a nice finished looking little transformer. And I was able to get all the windings on, so now I'll have to see if it works and how hot it gets. I've just made some wire posts to connect the test board to the transformer terminals. With this, I want to see if I'm close to the voltages I need and if this transformer will function good enough. I have 280 ohms on the 14-volt rail, 140 ohms on both the positive and negative 7-volt rails, and 24 ohms on the 5-volt rail. I'll set it to a nominal 24 volts of input. The 14 volts is good. Plus and minus 7, very close. And the 5 volts is about as close as I could ask to the 5.1 volts I was planning on. So I'm putting out almost 2.5 watts here, well over the 2 I need, and I'm putting in about 2.9 watts, so 400 milliwatts of waste. I don't think that's too bad at all. And it's not even warm. I'll have to let it run a few hours and see how it goes. But I think that's going to work fine, even better than I was expecting, really. The last parts to pick out are the linear regulators for the supply rails. Not a lot of choice for the negative regulators, so the negative 6 volt is the same series as I'm using for the final negative 5 volts. The positive 6 volts is different. The 5 volt regulator I'm using has a maximum input of 6 volts. The entire TPS 7A20 series is a maximum of 6 volts input. So I decided to go with this MCP 1801 series, can handle 12 volts of input, and is a high PSRR rated regulator. These two may not even get installed, but I'm going to make space for them. To feed the 3.3 volt regulator, I'm planning on using this 4.2 volt regulator. I do kinda like the TPS 7A20 series chips, so I'm shooting for 0.9 volt drop across this regulator, which will give me another 0.9 volt drop across the 3.3 volt regulator on the control board. That will give me maybe 150 milliwatts of heat for each of the regulators to handle. If it turns out to be too much, I'll get the 3.6 volt version and rewind the transformer. I think it will be fine. The 12 volt linear regulator was a bit harder to pick out than I thought it would be. Need to keep the input voltage at least 1.5 volts higher than the output for this regulator for good PSRR values, so no low dropout here. but it does have decent PSRR with at least a 4.7 microfarad output capacitor. It has at least a half a volt better dropout over the tiny 7800 series regulators, and I believe for the 7800 series to have a good PSRR ratio even need a bit more voltage difference input to output. So I went with this. Never used these before, so I'll see. It's only a 100 milliamp regulator, but I'm only pulling 30 milliamps. But not a lot of headroom on this one. I may put an alternate pad down just in case. So it's layout time, then get a PC board ordered, then a little bit of a wait. Thank you for watching.